so I'm going to talk a little bit about where we're going now. I call him a colleague, competitor, Francesco this morning covered the first couple of slides. Wouldn't surprise you to know that we're all heading in the same direction, and given the fact that the automotive, the silicon industry has to be about 2 or 3 years ahead of where the automotive industry starts. We've been thinking about this stuff for an awfully long time. You'll hear about my version of his slides. Okay, so we'll talk about the vehicle the developments, and then we'll talk about the real-time processes that we've come up with to address the challenge. Okay, so this is my version of his first couple of slides. We've got on the left-hand side here, we've got he described it as spaghetti. It's kind of a rat's nest of networks. That's a little bit unfair. It's not really a rat's nest, but it's not the way you would build a network if you were starting from scratch. We know how we got there. We started to add features to vehicles, and we just stuck them on the network. And what was the closest bus to get to? It was a CAN bus, and we stuck it on that, and so on. It's not the way to build networks. People have known this for a long time. There are papers going back to, 9 or 10 years ago where people said this is kind of a dumb way of building networks. So anyway, the transition is very much to domain and zone, as been covered this morning, and again you'll probably find a lot of commonality between what you heard this morning from ST, because we're all talking to the same people. Okay, so the focus starts to become on the vehicle infrastructure as a platform. Okay, so we begin to move away from this idea that there's lots of individual elements inside the vehicle, that you can provide a piece of electronics to do something for you. Okay, you have to start looking at it as an entire entity, and that really is a couple of effects. That the first effect is that number one, the OEM becomes extremely important. I was having some conversations with Ken actually earlier about the challenges that even getting things onto the network brought to the automotive industry. But now you really need to think about this stuff if you're an OEM, because suddenly a lot of your functionality is in a single place. And if you don't own it, then you need to think about who does own it. And the idea of just passing that off to a tier one to do it for you maybe isn't quite as attractive as it used to be. The second thing is that you then have to begin to look at how the software-defined vehicle begins to take shape and what that means for you. And there's clearly huge benefits that we heard earlier on again. A story I like to tell is that a colleague who took his car in for, I won't mention the German brand manufacturer, but took his car in for a service. They said, you've got an engine management software update. They did the engine management software, discovered it broke the car, and he needed to get a new fuel pump fitted to the car to fix the engine because the fuel pump software or something wasn't compatible anymore. This is a huge problem for OEMs logistically. So the idea of moving a lot of stuff into software is really attractive. It's a really nice thing to be able to do, but you have to think about this as a platform and where things are going. Okay, so we talk about the usual automotive stuff in terms of robust and safe and secure and all the rest of it. We want to make sure that we can upgrade things to fix bugs, to update security, and so on, but also to be able to offer features. I noticed, was it BMW were starting to charge for, was it seat heating or something? They could do, they feel people may want to pay maybe for seat heating in the wintertime, but not in the summertime. That kind of makes sense, right? So anyway, so we're going to be seeing more and more of that, and it's easier to manage optionalism across a car range and so on. So these are the kind of things that we're looking at. Now obviously when we talk about domain controllers and zone controllers, we're looking at integration. We're looking at integration of functionality into a single box. When we talk to people, sometimes that's a new box. They're just adding a box into the system. Sometimes they're integrating extra functionality into a box that already exists. And a lot of the cost benefits are not from the move away from this optionalism or reducing the number of boxes. It's simply that it's easier to manage and you don't need as many boxes on the shelves in the factories when you're building cars. Okay, so what are the key technologies that we think we need? And we've spent a lot of time thinking about this. We really think you need a lot of compute capability. It's got to be real time, probably, certainly in things like propulsion, and probably a lot of body electronics as well. It's got to be real time. Okay, so it's got to respond in a given way. If you put your foot in the gas pedal, you don't want a sort of iPhone response. Sometimes it's really quick to respond, and sometimes it's a little bit laggy because it's doing something else at the same time. When you put your foot in the gas, you want it to react the same way every single time. When you brake, the same. You want the car to behave in a very deterministic way, otherwise it becomes dangerously unsafe, potentially. Okay, we want to be able to isolate processes within the box that we've suddenly integrated lots of stuff in. And again, this was mentioned a little bit, but this morning I'll talk a little bit more about what we've done there. And the third thing you really need is resource flexibility, because when we speak to people, no two people are doing things in exactly the same way. Everyone's got their own slightly different idea of what should be in a domain, what kind of features are in a domain or a zone, that kind of thing. So we need a lot of flexibility inside these processors. So that's really what we're looking for, and that's what we decided to build into a processor. Now, there's two ways of doing this, really. If you're talking about hosting multiple things at the same time, a classic way of doing it is to put some nice, fast application class processors in there. Virtualization is extremely well established as a computing concept. It's been around for many, many decades. I learnt about it in university. That's how long ago this has been active. And then we'll throw in a couple of real-time cores for things that need to happen every 1 millisecond. Okay, that's one way of doing it. And if you're talking application cores, you've got to throw in your LPDDR memory and whatever else, and we've got lots of processors that do that kind of thing. The other thing which people hadn't really done up until this generation is just said, look, why don't we just take a standard microcontroller and put tons and tons and tons and tons of real-time performance on there by adding lots of cores and lots of the other features that you need for these kind of applications. So that's this kind of thing where you've got lots and lots of real-time cores, and either no application cores or it's more of a sideline feature of it. This is the marketing slide about what we announced at Embedded World just a couple of months ago. We think this is a new class of processor because it looks and feels a little bit like a microcontroller, and I'll show you the block diagram of features in just a second. It kind of looks like the microcontrollers we've been using for years, but the reality is there's a lot going on under the hoods that make these guys a little bit different. The first thing is, because we're now in 16 nanometer, we're going down to 5 nanometer. These are really fast. These are 1 gigahertz processors. So current generation, you probably get products in production which are 2 or 3 megahertz, 200 or 300 megahertz maybe, is kind of where we are. Just think if you could run that code at 1 gigahertz, what you could do with it. And that's really what we're looking at with these kind of applications as a starting point. And things are only really going to get faster and more powerful as we go. But let's dive into the details a little bit. I'm going to get through this quite quickly because all the marketing stuff has been done for me by ST, so it's great. This is a pretty standard kind of block diagram. What this doesn't show you is all the stuff that's going on under the hood to make this suitable for this kind of application space. So you can see we've got what we call real-time units. This is where we gather our Cortex R52 cores, so we're using the same cores as you saw earlier on. Cortex R52 is a real-time core, but it includes an extra, what ARM call an execution level, a hypervisor level. So it's got the user and supervisor privilege levels, if you like, which you've had in processors for years, and adds this third level, which then allows you to run multiple user supervisor clients on the same core. Okay, so you can have multiple AUTOSAR OSs running it, or an AUTOSAR OS and a bare metal, or an AUTOSAR OS and a FreeRTOS, or any combination of the above. And that's managed inside the core, and the core's got a virtual machine identifier and all that kind of thing, and we can use that. It's also got the Neon kind of linear algebra floating point engine. There's a couple of extra helper cores in here. There's a nice Cortex M33 which runs at 400 megahertz, which is just doing essentially housekeeping, safety management, that kind of thing. We'll get a DSP, 25 gigaflop linear algebra engine. Ethernet, CAN, the existing CAN, the one we've got, CAN FD in fact, and all the usual kind of other stuff, that usual sort of fairly standard kind of connectivity with the hardware security engine, which is updatable depending on any new attacks developed and all that kind of thing. But the key thing that this chart does not show is the fact that underlying every single element here is the concept of partitioning and of isolation. Okay. Isolation and partitioning is really easy to do on cores, particularly if it's a Cortex R52, where you already have this extra hypervisor execution level. You just write some software and you kind of manage the clients that way. Okay, that's great. So you can do the cores nice and easily. What about the other cores in the system? What about things like what I call the assistant managers? So things like DMA, things like the hardware security engine. What about them? Because they need access to the whole memory map, but you also want to be able to isolate those things, okay? This architecture takes that into account, and if any of these master cores, if you like, are using these assistant cores, what they do is they also pass on their privileges whenever they're asking them to do something for us. So that means that if I ask the hardware security engine to go and do some crypto work on a piece of memory content somewhere I've got, it can only access that memory content. It can never access anything else while it's working for me. If an alternative core decides to ask it to do something similar, it will only get access to its area of memory that it's allowed to. So these permissions are passed from master to master. That's all done in hardware. It's all done automatically. Nobody else gets a chance to interfere with it. Same for the DMAs. Of the 6 DMAs on this, individual DMA channels only get the permissions they're allowed. They're not allowed to go and interfere with anyone else's memory that doesn't belong to the owning entity, if you like. Okay. What about things like the Ethernet subsystem? Okay, we've got a switch on here as well. The switch delivers your Ethernet packets to 8 individual ports, so you can effectively have 8 isolated independent Ethernet owning activities going on here. How does it move the frame contents from the Ethernet receive into the memory that's got to go to? Well, again, it knows and it gets the same permissions that the guy who owns it gets. And again, that's inherent in the system. You don't ever have a situation where I receive a frame for core number 5 and it goes into core number 2's memory because of some kind of glitch. It just physically doesn't have access while it's handling core number 5's Ethernet frame. Okay. The other thing that's crucially important inside a system like this, of course, is safety. If we get some kind of safety fault inside the system, if it's a software fault, yeah, we kind of know where the fault occurred. Maybe we can handle it that way. What if it's a hardware fault? What if it's something like an ECC fault in memory somewhere? What do we do? Do we reset the whole chip and we lose all of the multiple applications that are running here? Or do we do what happens here, which is the entity which is using the memory at the time that the ECC fault occurred is flagged as having the fault. So the fault is tied into the individual partition which experienced the fault. Even if that memory is shared, which again is supported inside the system, if you have shared memory and someone is writing into memory and an ECC fault occurs, then only the person who's doing the writing gets the fault and they get a chance to handle it. Maybe they rewrite again, maybe they just say, okay, this is too dangerous for me, I'm going to shut down and restart. The person who's reading the memory is not affected because they haven't read the fault yet. And so they don't have to worry about a fault. So we've got a demo out there which shows you what can happen if you don't have these inherent support right throughout the system. So say cores supporting cores inside the peripherals where we can protect from interference and from faults, and inside the interconnect, obviously, to make sure that the permissions are passed around the system properly. Okay, so just to finalize, what does that look like once you get the system up and running? Well, it means you can do this kind of thing. It means you can take, a core. Let's say you've got an application, and yeah, you're taking a 2-core 300 megahertz system, and you want to port it in here. Well, let's just give it a 1 gigahertz core, or maybe give it a whole cluster, and give it lots, however much RAM we need, and how many DMA channels we need, whatever other features we need on it, and we're going to just ring fence all of those guys together, including I/O pins. I didn't mention I/O pins. You can also ring fence I/O pins in here as well. Okay, there might be a steering application which a single core will do. Maybe something like a BMS which you only have to manage and look at intermittently. Maybe it can run as a VM in a core. Again, even though it's a client running on an individual core, which may also be doing something else, maybe a range calculation, doesn't make any difference. Where that client's running, this is all it can see. And when this client is running on the same core, this is all it can see. Okay, so it's important when you're looking at these things to look at the totality of the architecture. It's not just what the cores are doing, because lots of people can mess up what's happening inside the chip. In terms of the software viewpoint, this is what you can see. On the R52s, you can run hypervisors if you want to have multiple clients running in a single core. Whatever firmware runs on top of that, real-time drivers, that would be things like your MCAL that we heard about earlier on. Any AUTOSAR, things like Zephyr are possible in these cores because they're fast enough. Whatever stacks that you want to run, motor control, AI, etc., and either AUTOSAR or non-AUTOSAR, depending on how you want to manage that. And then for the helper cores, similar kind of thing as you get on your existing architecture in terms of just a standard microcontroller kind of environment. Okay, so that's how we view the domain. A lot of overlap with what ST are doing with the Stellar family. Because we're on 16 nanometer going down to 5, we can run a heck of a lot faster. We can get a lot more done on the IC, but the direction of travel really is the same, and it really will involve creating a brand new world in terms of networks inside the vehicle. Okay, that's me, and I assume you'd heard of NXP, so I didn't give a company introduction, but if anyone has any questions.